In lecture today, we're going to talk about Taylor polynomials, which allows us to approximate functions using the Taylor series that we learned last week. But this isn't a new idea to us. We've been approximating functions since all the way back in Calc 1, which brings me to our warm-up exercise. Let's begin by finding the equation of the tangent line to f of x equal to sine x at x equal to 0. The derivative, f prime of x, is equal to cosine x, and at 0, f prime of x is equal to cosine of 0, which is equal to 1. F of 0 is sine of 0, which is 0. And now we have all the pieces we need to find the equation of the tangent line. Y is equal to 0 plus our slope, f prime of 0, is 1, times x minus x naught, which is 0. This simplifies down to y equal to x. For our second part of our warm-up exercise, when approximating f of x equal to sine x with y equal to x, what is the size of the error when x is equal to 0.8? And I gave the hint that this does not involve any calculus. The actual error is going to be the difference between our approximation and the curve itself, which in our case is x minus sine x. And we use the absolute value signs because we don't care if our approximation is an overestimate or an underestimate. We just want to know how big is the error. When we were doing error bounds last week, we were always finding a bound for the error. In other words, we would say the size of the error is less than the size of the next term. But here, because we can actually compute what sine of 0.8 or sine of 0.9 is, that means we don't have to estimate the error using the alternating series estimation theorem. We can find the actual error because we know exactly what the difference is between the curve and the approximation. At x equal to 0.8, the size of the error is equal to the absolute value of 0.8 minus sine of 0.8. Evaluating this in your calculator, we get that it is approximately 0.082644. At x equal to 0.9, the size of the error is equal to the absolute value of 0.9 minus sine of 0.9. Subbing that into our calculator, we get that this is approximately 0.11666731. Geometrically, what does this mean? Let's sketch a graph quick. In red, we have y equal to x. And in blue, we have y equal to sine of x. Let's plot x equal to 0.8. The error that we just found is the difference between y equal to x and sine x. On our graph, we have that the size of the error is approximately 0.082644. In the third part, we want to know for what values of x is the size of the error less than 1/10. In part 2, we found that at x equal to 0.8, the error is 0.082 something. And at x equal to 0.9, the error is 0.11 something. So we know that somewhere in this interval between x equal to 0.8 and x equal to 0.9, the size of the error is going to be 1/10. Algebraically, we would write this as the size of the error is equal to the absolute value of x minus sine of x, which we want less than 1/10. Unfortunately, this is not an equation that we can solve algebraically, so you would need to use your graphing calculator or some type of math website to solve this equation for us. When we do, we find that the absolute value of x is less than 0.85375. This makes complete sense based on our work above, where we knew the error was going to fall somewhere within this interval. If we wanted to approximate f of x equal to sine x with x, that's really only going to work for very, very small x. In other words, x has to be really close to 0. What if we wanted a better approximation, or we wanted an approximation somewhere other than at x equal to 0? We're going to explore that idea in lecture today. But first, let's talk a little bit of background on trig. You guys have never known a time where calculators didn't exist. Ever since you guys have been old enough to do trig, all you've had to do is press a few buttons on a calculator. But what about before calculators were common? The first pocket-sized scientific calculator wasn't even invented until 1972. And even then, it originally cost $395, which by today's standards is over $2,000 for a simple calculator. But what were the alternatives if you wanted to, say, calculate sine of 45 degrees? We can do that using basic right triangles. But what if we wanted to know sine of 46 degrees? Without a calculator, you'd have to use a reference book. You can sort of see in this picture, this is a big book. It's heavy, it's really thick, and it's full of nothing but tables and tables of trigonometry. But there's no way that everything that's inside of this huge book could fit inside of the memory of an antiquated calculator. Even our calculators today don't contain the full contents of one of these books. So how do they do it? And where did they get these tables from in the first place? They were all found using Maclaurin's series. We found last week that sine of x can be written as the infinite polynomial x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And it keeps going on. But adding up infinitely many terms is impractical. So instead, we can approximate with our partial sums. On our opening slide, we approximated sine x with x. Or, for an even better approximation, we could approximate sine x with x minus x cubed over 3 factorial. But why stop there? Maybe we should keep going and add x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Or maybe we should go even further. How do we know which partial sum to use? And even if we know which partial sum to use, how do we differentiate between one partial sum and another partial sum? Let's find a more precise definition for these partial sums. From last week, we were able to derive the basic equation of a Taylor series for a function f of x centered at x equal to a. F of x is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at a over n factorial times x minus a to the nth power. In its expanded form, you can think of this as a polynomial on steroids. It goes on forever and ever. While f of x equals the infinite series from 0 to infinity, we can approximate f of x with the partial sum from n equals 0 to k. Notice that this partial sum is a polynomial of kth degree. We call it the kth degree Taylor polynomial of f of x centered at x equal to a, and it's notated as t sub k of x. But how exactly do we find Taylor polynomials? We have three primary methods of finding Taylor polynomials. The first is truncating a known Taylor series. Secondly, we can find them from scratch by using the definition of a Taylor series to find the Taylor polynomial. That's what we call the table method. And last, there's more exotic approaches, such as incomplete multiplication or division of series. We'll do an example of each type in lecture today. For our first one, let's go back to sin x. We want to find the following Taylor polynomials by truncating the known Taylor series for sin x, which we have written out in its expanded form for us already. Copying down the series for sin x, we know we don't need all of those terms. So let's work our way backwards and erase the ones we don't need. We're getting close. We have 3 terms. Maybe we should stop there. But remember that we're looking for the third degree Taylor polynomial. K is the highest degree term, not the number of terms. So if we want the third degree Taylor polynomial, that means that the highest degree term should be x cubed. So we keep erasing, giving us the third degree Taylor polynomial is equal to x minus x cubed over 3 factorial. Similarly, for t sub 5 of x, we work our way backwards until we get to x raised to the 5th power, giving us the 5th degree Taylor polynomial is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. For the 10th degree Taylor polynomial, we work our way backwards. But when we get to x to the 11th, we realize that we need to stop at x to the 10th, and there is no x to the 10th. So what should we do? We know for sure that x to the 11th is too many terms. But there is a term after x to the 9th over 9 factorial. It just has a coefficient of 0, giving us 0 times x to the 10th. And so we have our 10th degree Taylor polynomial. Here we have y equal to sin x in red, and in blue we have y equal to x, which was our original approximation from our opening slide. As we increase the degree of our Taylor polynomial, we can start to see that our approximation becomes better and better. This is a pretty straightforward example because we were looking for the Taylor polynomial of sin x, and we already had the entire Taylor series written out for us. But what if we wanted to find the Taylor polynomial for a more complicated function? We'll try that in the next example. We want to find the 9th degree Taylor polynomial of f of x equal to x cubed times e to the negative x squared, centered at x equal to 0. This question can be asked in 2 different ways. In part A, you're given e to the x in sigma notation, and in part B, we're given an approximation to e to the x by writing out the terms in its expanded form. Let's start in part A by modifying our known Taylor series by subbing in negative x squared, giving us, on the left-hand side, e to the negative x squared equal to the sum from n equals 0 to infinity of negative x squared raised to the nth power over n factorial. We want to simplify this before moving on to the next step. The sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial. Let's multiply through by x cubed. On the left-hand side, we have x cubed times e to the negative x squared equal to, on the right-hand side, the sum from n equals 0 to infinity of negative 1 raised to the n over n factorial, multiplying x cubed by x to the 2n in the numerator gives us x to the 2n plus 3. Now that we have our Taylor series for x cubed times e to the negative x squared, we can find the 9th degree Taylor polynomial. Starting at n equal to 0, we have x cubed. When n is equal to 1, we have negative x to the 5th. When n is equal to 2, we have plus x to the 7th over 2 factorial. At x equal to 3, we have minus x to the 9th over 3 factorial. Since we're looking for the 9th degree Taylor polynomial, we stop writing out terms when we get to x raised to the 9th power. In part B, we're given that e to the x is approximated by the 9th degree Taylor polynomial, which is equal to 1 plus x squared over 2 factorial plus ... all the way up to x to the 9th times 9 factorial. Just like we can modify our series in sigma notation, we can also modify the individual terms. Let's begin by subbing in negative x squared, same as we did before. On the left-hand side, we have e to the negative x squared, but now on the right-hand side, we have to sub in negative x squared for every term. I already gave you the outline of this problem just so that you don't have to write quite as much. Subbing in negative x squared on the right-hand side, 1 stays the same. Subbing in negative x squared into x, I'm going to move this 1 over so I can make room for one more term, giving us a negative x squared. Subbing in negative x squared into x squared over 2 factorial, we have a positive x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial plus x to the 12th over 6 factorial minus x to the 14th over 7 factorial plus x to the 16th over 8 factorial minus x to the 18th over 9 factorial. In our next step, let's multiply through by x cubed, giving us x cubed times e to the negative x squared is approximated by the 9th degree Taylor polynomial, which is equal to 1 times x cubed is x cubed minus x squared times x cubed, we add the exponents, that becomes x to the 5th, plus x to the 4th times x cubed gives us x to the 7th, and that's over 2 factorial, minus multiplying x to the 6th over 3 factorial through by x cubed gives us x to the 9th over 3 factorial. And since we've reached the 9th degree term and we're looking for the 9th degree Taylor polynomial, we can stop here. Either method, we still get the same answer. I wanted to quickly mention the notation before we move on. We're approximating x cubed times e to the negative x squared with the 9th degree Taylor polynomial. But the 9th degree Taylor polynomial is equal to x cubed minus x to the 5th plus x to the 7th over 2 factorial minus x to the 9th over 3 factorial. So when you're writing out your solutions, make sure that you're using the appropriate notation. In our first two examples, we found both of the Taylor polynomials by truncating known Taylor series. But what if we don't know the Taylor series? Then we have to rely on finding the Taylor polynomial from scratch. Let's do an example of one of those. We're looking for the third-degree Taylor polynomial for f of x equal to x to the 2/3 centered at x equal to 8. Now, I wrote on the problem that we want to do this from scratch using the definition, or the table method as we like to call it. But what if I hadn't written that down on the problem? How would we know that this was the correct approach? Two different things we should think about. We only have 4 Taylor series memorized. 1 over 1 minus x, sine x, cosine x, and e to the x. And no matter how we modify any of those, we're never going to be able to get back x to the 2/3. We also know that using a known Taylor series only works when it's centered at x equal to 0. Anytime our Taylor series is centered anywhere other than 0, we have to use the table method to find that Taylor series. It's the same thing for Taylor polynomials. Anytime you're looking for a Taylor polynomial that's centered somewhere other than 0, you have to build a table. When n is equal to 0, we're starting with x to the 2/3. When x is equal to 8, the cubed root of 8 is 2, 2 squared is 4. And subbing that into our last column, we have 4 over 0 factorial times x minus 8 to the 0th power, which simplifies down to 4. The first derivative of x to the 2/3, let's bring our 2/3 down front. Subtracting 1 from the exponent, we have x to the negative 1/3. When x is 8, the cubed root of 8 is 2, and because we have a negative in the exponent, that means that the 2 has to go in the denominator. So we have 2/3 times 1/2. I like to leave it in its unsimplified form in this column so it's clear where our numbers are coming from. And then in the last column, I like to simplify. So our first derivative at 8 is 1/3 over 1 factorial times x minus 8 to the first power. For our second derivative, bringing the negative 1/3 down front, we have 2/3 times a negative 1/3, which is a negative 2/9 times x, and subtracting 1 from the exponent, negative 1/3 minus 1 is negative 4/3. Subbing in x equal to 8, we have negative 2/9 times the cubed root of 8 is 2, 2 to the 4th is 16. Because we have a negative in the exponent, that means our 16 has to go in the denominator. Negative 2/9 times 1 over 16. 2 goes into 16 8 times. 8 times 9 is 72. So that simplifies to negative 1 over 72 over 2 factorial times x minus 8, quantity squared. Our third derivative, we have negative 2/9 times a negative 4/3, giving us a positive 8 over 27 times x to the negative 7/3. Subbing in x equal to 8, we have 8/27 times 1 over, we know that the cubed root of 8 is 2. I'm just going to leave this as 2 to the 7th. In our last column, simplifying, that becomes 1 over 432 over 3 factorial times x minus 8 raised to the 3rd power. Since we're looking for the third degree Taylor polynomial, and we just found the term raised to the 3rd power, we can stop. One thing that's really nice about Taylor polynomials is that when we are using the table method, we don't have to look for a pattern like we did when we were trying to find the Taylor series, since we only need a finite number of terms. Keeping that in mind, though, that means that the same answer algebraically can be expressed many different ways. So just for continuity and to make our TA's lives a little bit easier, I want you to simplify the nth derivative at 8 in your final answer. That would be the 4, the 1/3, the -1 over 72, and the 1 over 432. For our final answer, we have that f of x is equal to x to the 2/3, which we're approximating with our third degree Taylor polynomial, which is equal to 4 plus x minus 8 over 3 minus x minus 8 quantity squared over 72 times 2 factorial plus x minus 8 cubed over 432 times 3 factorial. Let's take a look at this geometrically. In black, we have y equal to x to the 2/3, and in red, we have our third degree Taylor polynomial. Notice that at x equal to 8, f of x is 4, and when x is equal to 8, our third degree Taylor polynomial is equal to 4, and all of the other terms after cancel out. This will always be true, so it's a nice, easy way to check your work as well. That also means that when x is near 8, we have a pretty good approximation. If we wanted the approximation to be accurate near some other x value, we would want to use the table method, centering it at that x value. This example worked out fairly easily using the table method. Let's try another one. We want to find the third degree Taylor polynomial for f of x equal to tan x centered at x equal to 0. Unlike our last example, the derivatives in this one were not easy. And while we could find the third derivative, I certainly wouldn't want to have to keep going to try to find the fourth derivative or anything greater than that. Do we have any other options that we could fall back on? Let's try this again, only now we're looking for the fifth degree Taylor polynomial, so we really don't want to use the table method. So we can use what I call the exotic approach. We know that tan x is equal to sine x over cosine x. And we also know the Taylor series for both sine x and cosine x. Quick word of caution though. When you have the sum of a sub n divided by the sum of b sub n, that is not equal to the sum of a sub n over b sub n. That means that we can't simply simplify this algebraically. Instead, we have to write the series out in their expanded form. And from here, we do exactly what it looks like. We want to divide the numerator by the denominator. To do this, we have to use long division. It's also easier for this approach if we simplify the factorials. We have 1 minus x squared over 2 plus x to the 4th over 24 minus, we still have an infinite series here, so we want to include the dot, dot, dot. And that goes into our numerator, x. Instead of jumping right to the minus x cubed over 3 factorial, when you're using long division, you want to make sure that every powered term is represented. So even though we don't have an x squared in the numerator, we still want to write it in. So I'll add 0 times x squared minus, we have x cubed over 3 factorial. 1 over 3 factorial is 1/6 times x cubed plus 0x to the 4th plus 1 over 5 factorial is 1 over 120 times x to the 5th plus 0 times x to the 6th minus ... For long division, we look at each of the leading terms. 1 goes into x times. Multiplying x times 1 minus x squared over 2 plus x to the 4th over 24 minus ... gives us x times 1 is x. X times a negative 1/2 x squared is negative 1/2 x cubed. X times x to the 4th over 24 is positive 1 over 24 times x to the 5th minus ... Subtracting the second line from the first, we have that x minus x is equal to 0. Negative 1/6 x cubed minus a negative 1/2 x cubed becomes 1/3 x cubed. 1 over 120 x to the 5th minus 1/24 x to the 5th simplifies down to minus 1 over 30 times x to the 5th. And bringing down our terms with 0, we should add in the plus 0 x to the 4th and a plus 0 x to the 6th minus ... 1 goes into 1/3 x cubed, a positive 1/3 x cubed, and distributing 1/3 x cubed across 1 minus x squared over 2 plus x to the 4th over 24 minus ... gives us 1/3 x cubed minus 1/6 x to the 5th minus ... Subtracting the second line from the first, the terms with an x cubed cancel out. Negative 1/30 minus a positive 1/6 gives us 2/15 times x to the 5th, bringing down our term with a 0 plus 0 x to the 6th minus ... 1 goes into 2/15 x to the 5th, positive 2/15 times x to the 5th. And we could keep going, since this is an infinite series dividing into an infinite series, so we'll put a plus ... up here. But for us, we're just looking for the 5th degree Taylor polynomial, and we just got x raised to the 5th power, so that means we can stop here, giving us our solution that f of x equal to tan x is approximated by the 5th degree Taylor polynomial, which is x plus 1/3 x cubed plus 2/15 x to the 5th. What's nice about this method is that if we wanted to find a higher value of k for our Taylor polynomial, it's really easy to keep going however far we need to. I had initially mentioned that the exotic approach not only involved division, but also multiplication. So let's look at an example that involves multiplication. We want the 5th degree Taylor polynomial for e to the x sine x centered at x equal to 0. We already know the Taylor series for e to the x centered at 0 and sine x centered at 0. A quick word of caution though, the sum of a sub n times the sum of b sub n is not equal to the sum of a sub n times b sub n. Instead, we have to FOIL out the entire infinite series. The easiest way to do this is to group your like terms. There's nothing we can multiply in the first series times the second series that's going to give us back a constant. So the lowest power term we're going to have is an x, and there's only one way we can get an x. That's by multiplying 1 times x gives us our first term of x raised to the first power. Now let's look for all the terms we can multiply together that would give us back x squared. When we multiply x by x, that works and gives us x squared. And those are the only terms that will give us x squared. Looking for terms that we can multiply together to get back x cubed, starting with our 1, we can multiply that by negative 16x cubed. Since there's no even terms, there's nothing we can multiply x by to give us back x cubed. At 1/2 x squared, we can multiply that by x to give us back a positive 1/2 x squared times x. We've worked our way through examples of each type of ways we can find our Taylor polynomials. The idea behind Taylor polynomials, the reason why we care, is because they allow us to approximate functions. But just how accurate are these approximations? Let's take a look at our error bounds. This is the third time that we've seen error bounds in our course. We first encountered them back in the 4th week, where we were using the trapezoid rule. Then last week, we introduced them with the alternating series estimation theorem. And now we're going to apply it to Taylor polynomials. We're going to focus on series that satisfy the alternating series estimation theorem. There's 3 different ways we could ask these questions. We could ask how many terms do we need in order for the error to be less than some number. That's the smallest n. We've been doing that before. We could be asked to find a bound for the error, which we've also done before. Or, this is new now, we could be asked to find the domain of x. For what values of x will the error be less than a given number? You will always be given 2 and asked to find the third. Let's do another example. Going back to our f of x equal to sine x, let's find a bound for the error when we're approximating it with the 5th degree Taylor polynomial on the interval where the absolute value of x is less than 1/2. Alternatively, asking the exact same thing, we could just word it differently, saying find a bound for the absolute value of sine x minus x cubed over 3 factorial plus x to the 5th over 5 factorial when the absolute value of x is less than 1/2. This is very similar to what we did in the opening slide. Here we have y equal to sine x in blue and the 5th degree Taylor polynomial in red. And we're looking for the largest value that the error can be when x is between negative 1/2 and 1/2. Sine x is an alternating series, and so we can use the alternating series estimation theorem. The limit as n approaches infinity of x to the 2n plus 1 over 2n plus 1 factorial is equal to 0. This is clearly true, and it hinges on the fact that the absolute value of x is less than 1. Since we're dealing with a fraction, something less than 1, that means that we're going to have a 1 in the numerator and some number down here in the denominator. And that number down here is going to be positive and growing. 1 over something that's growing without bound clearly goes to 0 as n goes to infinity. Same idea behind why we can say that b sub n is decreasing. Since the absolute value of x is less than 1, x to the 2n plus 3 over 2n plus 3 factorial has to be less than x to the 2n plus 1 over 2n plus 1 factorial. Subbing in n equal to 0, we can also easily see that these terms will always be positive. Now that we've satisfied the hypotheses of the alternating series estimation theorem, We can apply it by saying the size of the error is going to be less than the size of the next term. The last term that we used in our approximation is x to the 5th over 5 factorial. So the next term is x to the 7th over 7 factorial. This is going to be less than the absolute value of x raised to the 7th power over 7 factorial. We're given that the absolute value of x will always be less than 1/2. So continuing with our inequality, we know that the absolute value of x to the 7th over 7 factorial is going to be less than 1/2 raised to the 7th power over 7 factorial. Evaluating this in our calculator, we get that this is approximately equal to 0. We have 5 zeros, 0, 0, 0, 0, 0, 1, 5, 5, 0, 9, 9. And if we wanted to round this, we could write this as 1.551 times 10 to the -6th. Same as before, you always have to round up because we're looking for a guarantee. We absolutely can guarantee that the error is going to be less than 1.551 times 10 to the -6th as long as our x remains within that interval from -1/2 to 1/2. So in part A, we're given the number of terms and we're given the domain of x. Let's move on to part B. We want to know for what values of x does the alternating series estimation theorem guarantee that our 5th degree Taylor polynomial will approximate f of x equal to sine x with the size of the error less than 10 to the -8th. Another way we can say this is find the difference between the absolute value of the sum from 0 to infinity minus the partial sum from n equals 0 to 2. Remember that the difference between the function sine x itself and the approximation, that is the error. So this part that's inside of the absolute value signs is the exact same thing that we have up here when we're saying size of the error less than 10 to the -8th. We've already satisfied the hypothesis in part A, so we can apply the alternating series estimation theorem, which tells us the size of the error is less than the size of the next term, which we want to be less than 10 to the -8th. Pay close attention to your inequality in these types of problems to make sure that it always makes sense the direction that you have them going. Since we're using the 5th degree Taylor polynomial to approximate sine x, the next term, the first one we're not using, is x to the 7th over 7 factorial. And we want this to be less than 10 to the -8th. We can rewrite this as the absolute value of x raised to the 7th power. Multiplying both sides through by 7 factorial, we have that this is less than 7 factorial times 10 to the -8th, or we could write that as over 10 to the 8th. Solving for x, we can take the 7th root of both sides, giving us the absolute value of x is less than the quantity 7 factorial over 10 to the 8th raised to the 1/7. Subbing that into our calculator, we have that this is approximately 0.24324848456. Let's think about how we should round this. We need to guarantee that as long as x is within this interval, then the error will be less than 10 to the -8th. If we round up, let's say we round up drastically, could we say that as long as the absolute value of x is less than 1, the error is going to be less than 10 to the -8th? No, that's absolutely not true. But what if we rounded down. If we rounded down and said, oh, absolute value of x less than 0.2, then would you feel comfortable absolutely guaranteeing that as long as x was between negative 0.2 and positive 0.2, that the error would be less than 10 to the negative 8th? Given our answer here, that's a pretty safe bet, which means that you should always truncate to avoid having an x value outside of the error bound, giving us our final answer of the absolute value of x less than, I'll just go to 4 decimal places, say, 0.2432. You must show this step. Why do we care so much about approximating sine x? We know the Taylor series for sine x. In the engineering of optics, lenses, for example, think the Hubble telescope. Formulas with a lot of trig arise quite frequently, and it's common practice to replace the signs in those formulas with the Taylor polynomial to make the computation simpler. But which Taylor polynomial do you think they use? Which one is simple and accurate enough? As long as x is small enough, close enough to 0, we can go all the way back to our opening slide, where we were approximating sine x with our first degree Taylor polynomial. Now you know enough to know exactly how accurate that approximation is. I included a few more examples in your lecture notes after this, just for you to have as reference. They're completely worked out. In example 8, you're modifying a known Taylor polynomial. Notice in part B that you take the derivative. In the examples we did earlier, we only did substitution and multiplication. But you can also use differentiation and integration with Taylor polynomials, the same way we did last week with Taylor series. Then the last example that I included for us is using Taylor series to prove the following limit identities. You might have proved some of these back when you were in trig or in geometry, and those proofs are quite involved. But using Taylor series to evaluate these limits, it becomes very simple and easy to prove the identities. So I gave you the solutions so that you can follow along, or I'd recommend that you try them on your own and then compare your answers. It's good practice. This concludes our section on sequences and series. In our next lecture on Wednesday, we move into an introduction into multivariable and vector calculus.